but it is as opposed to the isometric transformations that we've looked at. What does the term isometry mean? I ask this every time we go through a transformation. And yet, every single time I ask the question, nobody knows what it means. My hope is that, you come into this class, I expect that you don't know what the term isometric means, but I expect by the third time that I've asked that question in 3 different lessons that somebody might know what it means. Okay, it's the only way that we learn terms so that we can use them later on. Anybody? Isometry. Mick's doing the right thing. He's finding his way to the back of the book in the glossary section where he can read the definition to me. Brady's got it. Brady, what is an isometry?
It is a distance preserving transformation between metric spaces usually assumed to be bijective.
Okay. It's a really complex definition. Can you put that in your own words? When we talk about transformations, right, we have 3 types of isometric transformations. Brady, can you put it in your own words?
It's a congruent transformation.
Congruent transformation. Somebody elaborate on that. Caleb.
Rotation, translation, reflection.
Rotation, translation, reflection. All right. What is preserved from transformation to transformation, whether it's reflection, translation, or rotation? The size and shape. Size and shape don't change. You use the term congruent figures, right? So angles stay the same measure, side lengths stay the same side length. Orientation may change, depending if it is a reflection or a rotation. If it's a translation, orientation won't change. Dilation is not isometric, which means what? If something is not isometric and we're transforming it, what might change? The size. The size in particular, okay? But in this case, not the shape, okay? Size changes, not the shape. Have you ever been to an optometrist maybe to get your eyes checked? By a raise of hands, how many of you have been to an eye doctor to get your eyes checked? All right? Used to be that they would put a drop in your eyes, right? Now they put your head up to a machine and they have a little thing that goes and blows in your eye. Freaks me out every time. But what is that used to do? What are they trying to do to your eye, to your pupil? They're trying to dilate your eye. And so you've heard the term dilation probably most commonly in terms of, an optometrist, right? What are they doing to your pupil? Making it bigger. Is it changing the shape? Does your pupil suddenly become a square? No, that would be freaky, right? But they're making it bigger. Now, it's still proportional. It's still a circle, correct? But it's bigger. Does dilation mean to make bigger? No. Does not. It can mean that, but does it always mean that? No. You guys are in science classes, so you probably know something about some basic principles of physics, right? So there are certain terms that we use that we make assumptions on, how we use those terms, like the term acceleration. Does anybody know what the technical term for, or what technically acceleration means? Speeding up or slowing down, or any change in direction, right? Which means what we use the term accelerate to mean what? If somebody says accelerate, or their acceleration was, such and such, what do we typically think of? Going faster, all right? So, but in a scientific term, if we said stomp on the accelerator, what do we typically mean? Push your foot on the gas pedal, right? But if we use the technical term for acceleration, the accelerator could be the gas pedal, it could be the brake, it could be the steering wheel, right? Because it means any change in speed or direction, all right? Dilation just means this. It is a transformation that changes the size of a figure but not its shape. The multiplier used on each dimension of a figure to change it into a similar figure is the scale factor, meaning we can make it smaller if the scale factor is less than 1. Okay? We'll make it bigger if our scale factor is greater than 1. So if it's a fraction, if we multiply something by a fraction, are we making it bigger or smaller? Smaller. If I multiply something by 1/2, it's going to be half as big, right? So it's going to get smaller. A dilation maps a figure to a similar figure. Similar, meaning proportional. Okay, angles will maintain their degree, but the sides will simply be proportional. Okay? A dilation that results in an image smaller than a preimage is called a reduction or a contraction. Something contracts, gets smaller. Okay? Reduced in size. Okay? Dilation that results in an image that's larger is called an enlargement or an expansion. Those are terms that you want to know because they may want to say, hey, is this a reduction or is this an enlargement? Is this a contraction or is it an expansion? Okay, does that make sense? Those should be give-me's in how those terms are used. Okay, dilations require something specific though. If you remember back with our other transformations, translation required distance and direction, right? Reflection required a line of reflection. Rotation required a point of rotation, a direction of rotation, a degree of rotation, right? Required a lot. A dilation requires a point of rotation, okay, or a center of dilation. I probably said point of rotation. What I meant was center of dilation. The center of dilation is the intersection of lines that connect each point to the image with the corresponding point of the pre-image. C is the center of dilation. So if you'll notice that this guy right here, this is my pre-image, right? This is where I'm starting from. This is what I'm getting after dilation. Is this a reduction or an enlargement? Enlargement. All right. So depending upon what the scale factor is, what you'll see is that I'm getting further away from the center of dilation, right? In fact, I should be the same distance away as I am larger, right? So if it was a scale factor of 2, then x prime would be twice the distance as my pre-image x to c, okay? So this distance from x to x prime is going to be the same distance. Let's say I knew that this was 10, then this has to be 10 because the overall distance from here to the center is 20. Okay, if my scale factor is 2. So the distances between y prime and c is going to be the same distance, and I'm not saying that this is a true scale factor of 2 because obviously from here to here doesn't look to be the same distance, but that's how it should work. Okay? All right, hopefully I haven't lost you. But let's start working out some questions and see how we do. Let's see, looks like, I don't know if I pulled it up. Let's pull it up. Lesson 84. All right. Let's get over to lesson 84. I think I got it sent to you. I just didn't open it up here. All right, here we go. A photographer photograph measures 4 inches by 5 inches. We want to enlarge it by 200%. What are the new measurements? What do we need to do with 200%? Anybody know? Do I want to leave it as percent? Change it to a decimal. What is the decimal form of 200%? What is it? Nobody knows? Nobody knows? Convert 200% to... It's 2. So we're enlarging something by a scale factor of 2. 2 is the decimal. So what am I doing with 4 and 5? Adding 2, multiplying by 2. We're going to multiply by our scale factor. So what's 4 times 2? 8. What's 5 times 2? 10. So our new photograph is now an 8 by 10. Okay? It's going to maintain the same dimensions, right? 4/5 doubled is 8/10. Right? Okay, if I simplify that fraction, I should get back to 4/5. Okay? All right. Number 2, find the image of the rectangle after a dilation with a scale factor of 2 and a center of P. Scale factor of 2 and a center of P. This goes back to that picture of those 2 triangles that I showed you. Okay? Let's see. Look at A. Does A look correct? No, right? Because, I should be coming here And scale factor of 2 means I should be going that same distance, right, out again, right? All right, so it doesn't look like A. You guys can look at B from your screen. Let me scroll down and see it. Let's look at B. Does P look like the center of dilation? No. Okay. What about D? Does D look correct? What's wrong with D? What's that? You think it's too small? Right, because based upon this, right, here is my preimage, right? Here is my preimage here. So if I'm moving up by a scale factor of 2, then my image should be what in relation to my preimage? Should be how much larger? 2 times as large. So here where my cursor's at, this guy right here, that's my image. This is my preimage. Does it look like I went up by 2 or I went up by 1/2? Or really went down by half, right? All right, so D is a reduction. Does C look correct? Yes, right? So I'm going from here to here. I should see the same distance from there to there again. Okay, here to here, here to here. Same distance, doubled. Okay, there to there again. Okay, here to here, there to there. So I'm doubling that distance. Okay, so I should have a image that is double the size of my preimage. All right. Come on, clear it out. All right, here we go. All right, let's look at 3. Same kind of basic concept as that one. Find the image of the square after a dilation with a scale factor of 2 and a center of P. So notice this is that the center is actually on the square, right? So my image and my preimage should both have P on P, right? Okay. So does A look correct? No. Does C look correct? No. Let's come down here. Okay, we want a scale factor of 2 again, correct? All right, which one of those, B or D? I heard B, right? So let's look at this again, right? Let's see. So Q prime should be twice the distance away from P that Q was. Does that look correct? Okay. S prime should be twice the distance away from P as S was. That look correct? And R should be twice the distance away, right? Whereas over here, it is an enlargement, but it's not a scale factor of 2. Okay? Maybe like 1 1/3 or something to that nature. Okay, because anything over 1 is going to be an enlargement. All right, so this is a really good question here, and you'll probably see this on a test. All right, what this is going to show you is that if we do this on a coordinate plane, my image will actually move. Okay? All right, so we want to give the coordinates of the image of the triangle after a dilation centered at the origin with a scale factor of 0.2. So rather than really just drawing this, what I want you to understand is the first thing that we're going to do is we're going to write down what my coordinates are. Okay? What are the coordinates of H? 2, 1. And G? 10, 1. And F? 6, 6, 5. Okay, 6, 5. Now, if I want to apply a scale factor of 0.2, what am I going to do with each of those coordinate points? I think I heard somebody say it. Multiply by 0.2, right? So you guys have a calculator here, right? What is 2 times 0.2? 0.4, okay? All right, what is 1 times 0.2? 0.2. Okay, let's go to G prime. Okay, what is 10 times 0.2? 2. And what is 1 times 0.2? 0.2. Okay, what is 6 times 0.2? 1.2. Okay, 1.2. And what is 5 times 1 point, or sorry, 0.2? 1. 5 times 0.2 is 1? Okay. All right. So you can look down here and see, now granted you want to get these in order, 1.21, G was 2, 0.2, H was 0.4, 0.2. So we can look at this and get that, okay? But if we were going to end up graphing this, okay, what we're going to do this is, let's see, let's find some of these coordinates. 0.4, about there. Let's see, actually a little bit further away than that. Okay, 0.4 is a little over half, 0.2 is there. Actually, hold on, I'm using coordinate points, so a little tougher than it looks. 0.4 is going to go a little less than halfway here. 0.2, okay, is about there, and my marker's not quite right. And then on G, we're going to go to the right 2. We're going to be about there. And then we're going to be at 1.21. So what I see is I've got something that looks like that. Okay? So it's actually, it doesn't just make it smaller, but it actually moves it to a new location on the coordinate plane. All right? Like I said, you'll see a question like that on a test. Okay, 5 says on a sketch of a mural, 3 inches represents 1 foot. A door in the sketch is 2 inches by 5 inches high. What is the perimeter of the door in the mural expressed in inches? So let's do this first. Okay, on a sketch of a mural, 3 inches represents 1 foot. A door, okay, is 2 inches by 5 inches. Okay, the first thing that we need to determine here is what is the scale factor from the mural, or sorry, from the model to the mural. 3 inches represents 1 foot. So let's keep this in inches to inches, right? So how many inches are in a foot? So we're saying that 3 inches equals 12 inches, right? Okay, so it's 3 to 12. Can I reduce that? If 3 inches equals 12 inches, what does 1 inch equal? 4 inches, right? 12 divided by 3 is 4. So how much bigger is the mural than the sketch? It has a scale factor of 4, correct? Right? If 1 inch equals 4, whenever I take the sketch, I need to multiply everything by 4 to get the mural, right? Okay? So this is going to be, what, 20 by 8 inches? The question wasn't, though, it wasn't how tall it was or how wide it was. It said, what is the perimeter? So what do I need to do? I need to find the perimeter of it. 20 plus 20 plus 8 plus 8, or 40 plus 16. What's 40 plus 16? 56. Okay, so pay attention, because there's multiple steps in that. Okay? All right, what do we got? We got 9 questions. I'm probably not going to get through everything, but hopefully we've got basically the concept. If C is my center of dilation, I want a scale factor of 2. That means I'm going to go double the distance. All right, which means that length is going to be 12. All right, because this and this are the same, this and this are the same. It's going to double that length, which is going to make AB a mid-segment to that triangle. Yes? What's your question? What?
Like,
If I was closer to C?
no, like, it would always be going up.
Not always. Obviously, that would be a reduction. So let's say my scale factor was 1/2. Then I would cut the distance in half, and my length would be 3. Does that make sense? Okay. 7. Okay. 7. 7 gives me, I believe, a different kind of scale factor. Notice it says 175%. which is going to be a scale factor of what? 1.75, right? Convert percentage to decimal, move the decimal point 2 places to the left. Okay, so an artist is making a sketch of painting. Sketch measure 16 by 4. If the painting will be at 175%, what will be the lengths of the sides of the painting? So we're going to take 4 times 1.75. 4 times 1.75 is 7. 16 times 1.75 is 28. Okay. So how does the perimeter of the sketch compare to the perimeter of the painting? Well, what's 16? What's what? 32 plus 8? Okay, so the perimeter of the original was 40. 14 plus 56 is what? 70? So the perimeter became 40 over 50, or sorry, 40 over 70. So the perimeter has a scale factor of that comparison. Okay, sketch to actual painting has a perimeter of 4 to 7. You follow that? I know I'm trying to like rush through because I only got about 4 minutes here. Let's see. All right. So this is real similar to your question, Dylan. Will it always be bigger? No. This says use a scale factor of 1/2. Okay, so I have something like that where I'm looking at the distance. So half the distance approximately would be about right there. Okay, let's say I had a half the distance there and half the distance here. Okay, that would give me something that should look like it's the same picture. What are we? Did I call you Dylan? Oh, I'm sorry, Darian. All right, so this would be my A prime, my C prime, and my whatever D prime, or not D prime, but B prime probably. Okay, does that make sense? So you see how a reduction is applied by doing half the distance or a fraction of the distance. 9 is just like number 7 for the most part. You should get an answer of 1/3. Okay, the perimeter, the old perimeter to the new perimeter is going to be 1/3. Which makes sense because it's a scale factor of 3. The reciprocal of that is 1/3. All right, so I feel like you guys probably got enough there to get a pretty good start on your homework, and we will hit stop on this video.